In installment 6.5, we are going to look at force time graphs in greater detail. What we can see with each of these graphs is that their y-axis is force and the x-axis is time. So what we can read off these graphs is force and time, the gradient dividing those axes, delta F over delta T, which is the rate of change in force, and the area is F times delta T, which we recognize as the impulse, and also happens to be equal to the change in momentum. So now let's look at the first graph more closely. We'll do an Oiz-Zerga on this. And we've already done the RGA part, but we'll do it again. The origin in this case, we have 0. Y-axis is force, x-axis is time. And the intercepts, we have a y-intercept, which is f0 equals some positive number. The x-intercept, there is none. And of course, we read force time, the rate of change in force, delta F over delta T. And the area is F delta T, which is the impulse. So I want to focus in on finding the area of the impulse. And the area we are looking for I'll trace out here in green, is the area of a triangle, or of a rectangle, excuse me, is the area of a rectangle, and that is the area of a rectangle, which is length times width, and in this case we've got time times the force, and we know that's the impulse, so I'm just going to use commutative law to rearrange those. F times delta T. And if we remember, delta T is T minus T0. And in our case, T0 is 0, so delta T equals T. So Ft, F delta T are equivalent in this case. And so we are then simply just finding the area in here. Now, looking at what happens to this force, the force is constant. It is constant, and that constant is equal to the average force. If you remember, when we define impulse, we said it's the average force times the change in time. So when the force is constant, that is the average force. So we can just use that in our formula. Looking at our second example, we have some differences. So we have our Oiz-Zerga, and the big thing is the intercepts. So our origin starts at 0, 0. And we have force and time. And our intercepts, our y-intercept tells us that at time 0, the force is 0. And our x-intercept, there is a time where F does equal 0. It increases up to this maximum value at a constant rate, decreases down to a 0 there. And so again, we can read force and time. The gradient is the rate of change of force, and the area is the impulse, J. And the area we are looking for is the area of this entire triangle. So that is the area of a triangle, which is 1/2 base times height. And that is our impulse. And so the base, we have delta T. And the height, in this case, is F max. So I'm going to do a little bit of commutative law again and rearrange the order. 1/2 F max times delta T is going to be our impulse. Well, let's look geometrically diagrammatically what 1/2 F max means. Well, if this is F max and this is 0, 1/2 F max, or F max over 2, F max over 2 is really the average of the forces. And since it's changing at a constant rate, that F max, 1/2 F max, looks like this. So what we're doing is taking this value, 1/2 F max, keeping it as a constant and multiplying it times the change in time. If we look at the areas here, if we take this area, notice that is equal to this area. So if we fold that over this inflection point here, those areas are equal. And we'll notice that this area here is equal to this area here. And we fold that over, and that inflection, they'll be equal areas to each other. So the area of that triangle equals the area of that rectangle whose new height is the average force, F max over 2. Okay? So we are left with the average force times delta T again in this particular case. But we would go about finding it by taking 1/2 the maximum height times that time, or simply finding the area of the triangle. In our third case, we have force varying in a very odd way, and we'll do our oizerga with our focus on the intercepts. Our origin is 0, 0. Y-axis force, x-axis time. Our y-intercept in this case is some positive number, so F0 is some positive number. And the x-intercept, there is a time where F equals 0 over here. Again, we read force time. The gradient is the rate of change of force, and the area is the impulse J. So how do we find the area in these cases? Well, we don't have a smooth geometric. We can't just use the constant force. It's not constant. We can't easily find the average force. In the other case, in the previous case, we could, because force was changing at a constant rate. So the mathematical average of F max and 0 gave us that midpoint. But when it's this other function, it's hard to find out what the weighted average is to get us that average force. So we can't really do that either. So what we can do is we can break this up into little pieces and find the area of those little pieces. So we can take the sum of the area of the little pieces. And some of those areas will be the F value we use times the delta T's. Like so. Now we could use the right end, the right side as the F value, which will give us an over estimate of the area. We could use the left edge, which would give us an underestimate. Or we could use something closer to like the midpoint. And this will give us a more accurate value. But it is still going to be off. It is not going to be mathematically perfect as it would be over here. And if you notice, what we're doing here is we have this triangle like this, and we're finding the midpoint. So it will give us more accurate values. But as we made these delta T's smaller, so as delta T goes to 0, the accuracy increases. So that when delta T equals 0, we have perfection. However, when delta T is 0, anything multiplied 0 is 0. And of course, this is why Leibniz and Newton invented calculus. In particular, the integral, which is a summation in this particular case. So it becomes very important for us to know what f of x is so that we can integrate it. So in physics, when we collect data and we have a smooth curve over, it's important for us to find out what that function is so we can find other important values, either from the slope or the area. But in this case, in our tool, since we don't know f of x, we are relegated to this geometric approach, which is to break it up into little areas and add them up, and that will give us an approximation. And so that is our third technique. So that ends our treatment of force time graphs, wherein we saw what happens when we have a constant force, how we find that area, what we do when we have a changing force at a constant rate, how we find that area, and thirdly, what happens when we have an unknown or unconstant rate, how we would approach that geometrically, and of course, those of you in calculus could do it using calculus if we knew f of x. So in our next installment, 6.6, we are going to look at bouncy collisions in more detail.